Gear up, everyone. Today, we're dropping right into the tactical side of tech. Let's do this.
Hello friends! Welcome to my YouTube channel, Behind Enemy Code, Pythoning by Sachin.
So the only question left is, are you ready to learn, code, and grow? Let's go.
All right, let's dive right into this explainer and demystify the whole black box of artificial neural networks. Today, we're going completely under the hood to build one from the ground up, looking at the exact architecture that acts as the foundation for modern machine learning.
You know, it's a completely fascinating question, isn't it? We hear about AI learning all the time, but what does that actually mean in reality? Well, to answer that, we're going to look strictly at the highly optimized mathematical operations that make it all happen. Sure, it's deeply inspired by our biological nervous systems, but practically speaking, it's an incredibly elegant sequence of computations.
So here's our roadmap for today. First, the anatomy of a neuron. Then network layers, comparing topologies, how networks learn, and finally, real-world AI.
Okay, Section 1, Anatomy of a Neuron, the atomic unit. Let's start right at the microscopic level, because this individual node is the core computational unit of any neural network.
The core mechanism here is actually incredibly simple. Every single neuron receives inputs, and those connections are governed by weights. You can kind of think of weights like volume dials. A higher weight means a specific input feature has a massive influence on the final output. If an input is connected to a node, it's mathematically multiplied by this weight.
But weights alone aren't quite enough. We also have biases, which act a lot like baseline shifts. Think about it. If we didn't have a bias term, our calculations would be forced to pass directly through zero. Biases ensure the network has the mathematical flexibility to model complex patterns that don't precisely pass through the origin. It essentially gives the network the freedom to shift its activation threshold left or right. Now, this is where the architecture gets its real power. Without activation functions, this whole setup, no matter how deep you make it, would just be a basic linear regression model. It wouldn't be able to learn anything complex. Activation functions like ReLU, sigmoid, or tanh introduce non-linearity. They take that weighted sum plus the bias and transform it so the network can learn high-dimensional complex boundaries. ReLU, for example, simply outputs the maximum of 0 and our input, which, by the way, is incredibly computationally efficient.
Section 2, Network Layers, Sequential Organization. Now that we've got our individual parts, let's zoom out a bit and see how these neurons are arranged macroscopically.
Data flows cleanly through this architecture like a highly efficient assembly line. First, raw data enters the input layer. And get this, the number of neurons here must exactly match the number of features in your data set. So say you have a 28 by 28 pixel image. Well, that needs exactly 784 input nodes. Then the data moves into the hidden layers. This is the heavy lifting machinery. Early hidden layers might learn basic edges and shapes, while the deeper layers combine those into really complex abstractions. Finally, the output layer delivers the final classification or continuous value, like maybe using a softmax function to give us a probability distribution across multiple categories.
Moving right along, Section 3, Topologies Compared, Structural Blueprints. Changing these structural blueprints drastically alters what a neural network is actually capable of doing.
Take a standard multi-layer feed-forward network, for instance. It pushes data straight through in one strict, unidirectional path. It's absolutely fantastic for tabular data or general nonlinear classification. But then, compare that to a recurrent neural network, or RNN. An RNN does something totally different. It feeds the output of a neuron back into itself for the next time step. It introduces feedback loops. This gives the network an internal state, or a memory, making it completely perfect for sequential data, like natural language processing or time series predictions.
Section 4, How Networks Learn, the Training Engine. Look, architecting the nodes and layers is only half the battle. The network still has to adapt its internal parameters to actually learn anything useful.
And this dynamic three-step learning engine is where the real adaptation happens. The network is continuously adjusting millions of parameters through a rigorous, cyclic optimization routine. Step 1, forward propagation, where the network makes a guess. Step 2, it measures its mistake. And Step 3, it uses calculus to correct itself and update all those weights.
So let's zero in on Step 2 for a second. When the network outputs a prediction, it compares it against the true value using a loss function. For regression, this might be mean squared error. For binary classification, maybe binary cross-entropy. The absolutely crucial takeaway here is that minimizing this calculated loss is the fundamental objective of the entire training process. Simply put, the lower the loss, the smarter the network. Which brings us to the whole shebang, Backpropagation. This is the heart of machine learning. Relying heavily on the chain rule of calculus, the algorithm works in reverse. It goes from the output layer all the way back to the input layer to identify exactly which weights contributed most to the error. Optimization algorithms, like stochastic gradient descent, use a learning rate to take a step and update those millions of weights in the exact opposite direction of the error gradient. It literally nudges all those volume dials until the system gets it right.
Finally, Section 5, Real-World AI, Industry Dominance. We have the architecture, we have the learning engine. Now let's connect this intense math directly to reality.
The modularity of this architecture is just astounding. In computer vision, we use specialized convolutional neural networks, or CNNs, to efficiently capture spatial hierarchies in grid-like pixel data. In natural language processing, RNNs and modern transformers, using attention mechanisms, are powering the massive language models currently taking over the internet. Over in financial forecasting, deep recurrent networks and LSTMs are used extensively for algorithmic trading. And autonomous vehicles? They're using complex ensembles of all these architectures to process multimodal data from LiDAR, radar, and cameras simultaneously. This architecture isn't just theory, guys. It is the living, breathing foundation of modern AI.
Which brings us to our final thought. I really hope this explainer has given you a rock-solid blueprint of how these microscopic nodes, weights, and layers combine with sheer mathematical optimization to create intelligence. It truly leaves you wondering, if today's networks can hold deep conversations and steer autonomous cars safely through city streets, just how far will deep learning take us next?